Hello, statisticians, here for a probability overview. So I'm going to go through the study guide. The study guide doesn't have a ton in it here, so I'm going to run through just some examples on the side as I go through it. But couple starts out here with a couple general probability rules. And first is that the probabilities have to be 0 or greater on the low end. So just obviously you can't get any negative numbers. Um, and so you got to be hyper aware of just recognizing when you get a negative number that clearly doesn't make sense. And then on the other end, just remember that the probability of any event also cannot be greater than or equal to one. So excuse me, greater than one has to be less than or equal to one. So representing 0% to 100%. So keep that in mind. Number two, probability of all possible outcomes would equal one. Again, that just means the whole sample space. So all the possible. So for instance, when you roll a dice, 1, 2, 3, 4, 5, 6, the probability of getting one of those values, any one of those values, is going to be one. If you eliminate that rare chance that it somehow stays on its edge or something. Um, but heads or tails, again, the probability of getting a heads or a tails is going to be one. Um, again, presuming that it's not going to land on its edge. Couple things now with 3 and 4. Mutually exclusive. First of all, mutually exclusive really means, and there's a definition a little more down lower here, but um, just two events that cannot occur simultaneously. So mutually exclusive would be like heads and tails, or it would be like odds and evens on a die, or red cards and black cards in a deck of cards, where if you pull a red card out of a regular deck of cards, that means you didn't pull a black card. Okay, so the probability of both happening is 0, and then the probability of getting one or the other is just the sum. So for instance, the probability of rolling a 1 or a 2 is just going to be the probability of rolling a 1 plus the probability of rolling a 2. Because there is no overlap, there isn't anything else with that. So it'd be just 1/6 plus 1/6 in that situation. If there is an overlap, then you have to subtract that overlap. Um, so for instance, the probability of getting a red card or a heart would then be the probability of getting a red card, which would be 26 out of 52, plus the probability of getting a heart, which would be 13 out of 52. But then you've just counted the hearts twice, so you'd have to subtract the probability of getting a red card and a heart, which of course would be um, the double counted values there. So since the red cards also counted the hearts, so you would be subtracting the overlap there. See that a little bit later with a Venn diagram. Finally, complements. Complements is the idea that is really that if you break up the sample space or all the possible options into two groups, and where complements come in especially handy is if you take a scenario like you flip a coin 20 times, what's the probability that you get at least 3 tails? Well, you could figure out the probability of getting 3, 4, 5, 6, 7, 8, 9, 10, and so on tails, or you could just do 1 minus the probability of getting 2, 1, or 0. So when you see the term at least, that's a high probability that it's going to be a complement problem, just based on historical AP exam questions. Um, so that's complement, and that little superscript C stands for complement naturally. Big concept out of this unit is independence. Okay, so we'll get into independence here next. And independence is really the idea that one trial or some occurrence or some characteristic does not influence the next. And so when you look at what this notation right here means is this is the probability of A, and then that vertical line stands for given. So the probability of A given B, does that equal the probability of A? And then A and B, of course, represent events. So for instance, the probability of getting a heads, given that you just got a heads, is going to equal the probability of getting a heads because flipping a coin one trial to the next is independent. Or the probability of rolling a 6, given that you just rolled a 6, is the same as the probability of rolling a 6 because they're independent. So that's the idea there, is that there's not an influence. Now, if you were to look at it in a different sense and say, um, for instance, what's the probability that somebody is a Republican or a Democrat? And then check that same probability given that they're a certain gender, that would not be a situation where it's independent because polling numbers have shown historically that genders are not completely independent of political preference, that one gender has a preference for one party and another gender has a preference for another party, um, just based on general probabilities. And so that's a situation where the given statement, so for instance, the probability of being a Republican given that you are a female, is different than the probability of just being a Republican in general. Um, so that's, and we'll get into an example of that here as well. Um, Actually, um, I'll jump into this formula here. This is just another way of showing independence. If this is equal, then that shows that A and B are independent. So we would look at the scenario, we get the information of the probability of, for instance, being both female and Republican, and seeing if that does in fact equal the probability of being a female, at least a voting female in the United States, times the probability of being a voting Republican in the United States. And if those are equal, then we know that those were independent. If they're not equal, they are not independent. Now, note the real strong threshold there. This is like the equivalent of having a p-value of 1 in a chi-square test. There is no room for error here. It's not about having them be so different. It's just about them having be different at all is what we're really looking at with these formulas. So for instance, when we get to the second page here, I'll show that on a two-way table, or a table that you'll see at the bottom of the next page. Moving forward here, the example I already talked about rolling the die. So moving into just mutually exclusive or disjoint here, this is a situation where you can see there's no overlap between A and B. So we see the probability of A and B is 0 there, and the probability of A or B is just the sum of the two. S here would just stand for sample space. Note that this would not be a complement situation because there's A, B, and there's other stuff out here. Okay, a complement would truly be that there's this space and we have A and A complement. Okay, there is no other space in the whole sample space if this whole thing is S here, is the sample space. Okay, so complement means it's one or the other. Disjoint or mutually exclusive means it's one or the other, or it could be something else. On to the idea of not being mutually exclusive. Venn diagrams do a great job of showing this, of not being mutually exclusive. And what you see in this is this overlap here is important when it comes to the idea of not being mutually exclusive, because that 5 represents families that who have both a dog and a cat. So if we just look at some probability calculations out of this, the probability that a family has a cat here, keep in mind there's 30 total families we're talking about. You do have to keep in mind that the probability that a family has a cat is 15 out of 30, or 1/2 here, because that 5 is cat families. They just happen to also be dog families. So the probability that somebody's got a cat and a dog would then be the 5 there, the 5 out of 30. Okay, the probability that somebody has a cat or a dog, you have to be careful here. A quick way to look at that is, well, we see 8 families that have neither. So the quick answer to that is 22 out of 30. But if you'll see here, 22 is the sum of all 3 of these. Or if you look at, there's 15 cat families, there's 12 dog families. But again, we've now double counted the overlap. So we have to subtract that double count because that 5 is part of the 15 and it's part of the 12. And so we look at that, 27 minus 5 is 22, or 22 out of 30. So really, I should have written this as 15 out of 30 plus 12 out of 30 minus 5 out of 30, which is exactly what you see right here. The last thing, just to talk about the conditional piece, let's just talk about one here. Probability that somebody has a cat given that they have a dog. Okay, so this given, again, this line right there, that means given. So out of the dog families, so we've changed, now we aren't talking about all 30 families, we're just talking about given that they have a dog. So that's out of these 12 families that have a dog right here, how many of them also have a cat? Well, that would be 5 out of 12. Okay, so those are some probability questions you would get with that. In order to check independence here, you could check simply, is the probability that you have a cat, does that equal the probability that you have a cat given that you have a dog? And cat here we saw was 15 out of 30, and cat given dog we saw was 5 out of 12. Those two are not equal. We convert them to decimals just to make that clear. So having a cat and dog, having a cat and having a dog are not independent events here. Um, so in other words, it does influence. As you can see, the chance that somebody had a cat was lower if they had a dog because it was less than 50% in this example, and it was 50% here. So if you had a dog, you were less likely to have a cat. Other probability models that you'll see, tree diagram's a big one, especially when you have successive events. Okay, so this is obviously showing two flips of a coin, that the four results could be heads heads, which is a 1/4 chance of happening, heads tails, which is a 1/4 chance of happening, tails heads, and tails tails. Now, a couple things about this. One, doing these calculations at the end can be very helpful. They give you just specifics of the likelihood of each set of events, and it's especially helpful if you have something where it's not exactly 50-50. And so if we have a tree diagram where this is 70-30, and this is maybe like hockey and don't like hockey, okay, I'll put hockey complement, and this is you've been to a game and you haven't been to a game. Okay, and this is you've been to a game and you haven't been to a game. Again, that's always the same, just with the other result. And for this group, it might be 20% and 80%. Okay, and so what you would see then is 0.7 times 0.9 means that this is 0.63, this is 0.07, which is 0.7 times 0.1, 0.3 times 0.2, gives you the 0.06, and then 0.3 times 0.8 gives you the 0.24. So when you look at that overall, 63 and 7 is 70, which is exactly what that is. 24 and 6 is 30, which is exactly what that was. And so it all adds up to 1. And you could even turn this into a little diagram here where we say hockey, no hockey, like hockey, don't like hockey, game, no game. And notice how I went to 2 decimal places there. So that's tenths hundredths. So if I just say, let's pretend this was 100 people, then 63 people liked hockey and went to a game. 7 people liked hockey but didn't go to a game, which is that one there. 6 people didn't go to hockey but don't like hockey but had been to a game. And then 24 people don't like hockey and have never been to a game. And now this is, you can see this is the 70-30 of the people who went to hockey. And I'm going to show you what's really nice about this. This is 69 and 31. Is now if I were to ask you, given that somebody has been to a game, what are the chances they like hockey? Okay, so what I'm really asking is, what are the chances you like hockey given that you have been to a game? Now, this is tricky because if it was flip-flopped, given that you have been to a game, what are the chances you like hockey? Well, that's, given that you like hockey, what are the chances you've been to a game? That's just going this way. So given that you like hockey, there's a 90% chance you've been to a game. Given that you don't like hockey, there's a 20% chance you've been to a game. But now this is going backward. Okay, so this is going now, we got to see how many people have been to a game. Well, on here, that's the 63 and the 6, which here is just the 69 people, given those 69 who have been to a game, how many of those 69 liked hockey, which is what we asked here up in this spot, and it was 63. So the answer there would be 63 out of 69, whatever that corresponding decimal is. And so you can see that's that's a little tougher problem if you're working on the tree diagram, because you got to figure out, well, this is our denominator on the way right side, and then work back and think, well, this was the group that liked the hockey, this group didn't like hockey, and so that's why it's 63 out of 69. Now this conversion, sometimes it's easier to just leave it in tree diagrams, sometimes it's easier to be in the table. And the table here I'm going to end with, so this is called a two-way table. These values here and here are called marginal distributions, which just means they're the sum of the columns and the sum of the rows. Now, questions you could get out of something like this is it could simply be, what's the probability that somebody's male? Well, the probability that somebody's male would be 60 out of 240 here, because the male is 60 out of a total of 240. What's the probability that they drive a sports car? Well, that would be the 84 sports car drivers out of the 240. Okay, you could ask or questions, male or sports car. Okay, well, male was 60 out of the 240. Sports car was 84 out of the 240. But now, again, we have counted an overlap. this group right here got counted in both the male and the sports car group. So we'd have to subtract that 39 out of 240. And again, this would then be out of 240, and we just would add up the numerators. So we have 144, 105, it looks like. So there'd be 105 who were male drivers or drove a sports car. You could get an and scenario. Okay, male and sports car. This is a little easier because that just is the 39 who are male and sports car. Okay, the one more is looking at this with independence again. If I were to look at, again, I'm going to write this as driving a sports car, and does that equal the probability of driving a sports car given that you're male? The reason I like this is I think it's easier if you can see a cause-effect relationship, which in this case we're looking at gender perhaps as the cause and car as the effect. It's not always easy to find in a two-way table, and sometimes you could argue it goes either way. But in this one, you would kind of look at this as being the effect and then the effect given the cause. And so I think that makes it a little easier to look at. So really quickly here, with this calculation, the sports car would be the 84 out of 240. But now again, this given means we're not talking about the 240 as a total. The given, again, it's not a fraction bar. This is a vertical line, but we're talking about now out of the male group. So now our denominator is 60. So out of the males, what percent of them drive sports cars, which is 39. Okay, so 84 out of the 240 in this case is about 35% of this whole sample drive sports cars. Again, there's a question mark here. And out of the males alone, you can see clearly more than 35% drove sports cars. This was actually 65% of the males drove sports cars. So we see clearly here that the gender is not independent of car preference. 35% in general drove sports cars. Of the males, 65% drove sports cars. You can see the females would be much heavier on the sport utility vehicle side. Again, we've done something like this with the chi-square test for independence. This is just a different way of looking at it. But again, now we're looking to see if they're exactly equal, which would be like a p-value of 1 again, versus if there's any distinction or any difference. And sometimes you might set a threshold of that difference, but really what we're looking at here is equal or not equal. So once they were off by even 0.5% or less even, that was already too much. And so here they were clearly off by 30%. So you would say therefore, and then you'd add context to this, but you'd say they are not independent of each other based on that information. Leave it at that. Please, again, follow up with any questions if you have them. Thanks for listening.